Okay, so in the previous video we saw that with determinants, the following product rule holds. The determinant of A times B is equal to the determinant of A times the determinant of B. In this video we want to see some of the consequences of this product rule. What does it get us? Okay, so here's the first one. This tells us something about the determinant of an invertible matrix. Okay, so if I have an n by n matrix, then I can determine whether or not that matrix is invertible by computing the determinant. Right? This result says that I compute the determinant. If it's equal to 0, I know that A does not have an inverse. If it's not equal to 0, I know that A does have an inverse. Okay, and also I get a formula for the inverse. It's sitting right here. So how do I show this? Well, suppose A is invertible. So that means that A inverse exists such that A times A inverse equals the identity. But we can take the determinant of both sides of this equation. The determinant of A times A inverse is equal to the determinant of the identity. And what does that tell us? Well, we know that the determinant of a product is the product of the determinants. And we know that the determinant of the identity is just 1. Okay. Well, that tells me right away that the determinant can't be equal to 0. Why? Well, if it was equal to 0, then I would have 0 times something equal to 1. We know that's not possible. Alright, so the determinant can't be equal to 0. And since it's not equal to 0, I can divide both sides by the determinant of A, and I get that the determinant of A inverse is 1 over the determinant of A, which is what I wanted to show. Okay. Now, if A is not invertible, actually we saw that on the previous video in our argument for the product rule. If A is not invertible, then its reduced row echelon form is going to have a row of zeros, and we know that the determinant of that matrix has to be 0, and then kind of coming back to A involves a series of elementary row operations, and none of those elementary row operations can change the fact that the determinant is 0. So we get both possibilities. If A is invertible, the determinant can't be 0. If it's not invertible, the determinant must be 0. Okay, that's why we get the if and only if up here. All right, let's do an example to see that this works, and give us some more practice on computing inverses. Let's do a 3 by 3. Let's be I don't know, ambitious. Let's try a 3 by 3 example. Okay, 0, minus 1, 4, minus 2, 0, 3. Let's do that guy. Okay. So what's the determinant of A? Well, if I'm smart, I'm going to expand along the third column here, right? 0 times the 1, 2 minor minus 1 times the 2, 2 minor. 0 times the 3, 2 minor means I can do minus 1 times minus 1 to the 2 plus 2. There's my sign factor times this determinant. 1, 2, minus 2, 3. Okay. So I get minus, and here I get 3 plus 4. So I get minus 7 for the determinant. Okay. So I get minus 7 for my determinant, and in particular, minus 7 is not equal to 0. That tells me that A must have an inverse, and so I can go looking for that inverse. Okay, how do we find the inverse? Well, it's the usual algorithm. 0, 2, 0, minus 1, 4, minus 2, 0, 3, 0. Alright, to save space, I'm not going to write out all my row operations. So what's the first thing we're going to do? First thing we're going to do is use our leading 1 to get rid of that minus 2. And you know what, while we're at it, let's change signs in the second row. -4, 0, 0, 0, and 2 plus, so I'm going to get a 6 there, is that right? Oh, sorry, this was a 3 down here. All right, let's fix that. Okay, that's a 3. Okay, so I get that 7, right? And then over here, I'm going to get 2, 0, and 1. Okay, divide by 7. 1, 0, 2, 0, 0, 1 minus 4, 0, 0, 0, 1, 2 sevenths, 0, 1 over 7. And then I got 2 more row operations to go. I got to get rid of that 2, 1, 0, 0, so minus 2 times row 3. 1 minus 4 sevenths gives me 3 over 7, 0, minus 2 over 7, and 0, 1, 0. And so I'm going to get 8 over 7 minus 1, 4 over 7, 2 over 7, 0, 1 over 7. So that suggests that my inverse should be, and let's put that 1 over 7 out front, 3, 0, minus 2, okay, 8, minus 1, 4, 2, 0, 1. So what is the determinant of A inverse? So the determinant of the inverse should be, well, I can write, so A inverse is 1 over 7 times this guy. And remember from the last video that if I want to compute the determinant of a scalar multiple of a matrix, because I've got that 1 over 7 in every row, and oh, let me just fix something, right? That minus 1 needs to become a 7. Because that 1 over 7 is in every row. When I pull it out of one row, I get a 1 over 7. When I pull it out of the other one, I get a 1 over 7. When I pull it out of the third one, I get a 1 over 7. So I get 1 over 7 3 times. So it's 1 over 7 cubed times the determinant of 3, 0, minus 2, 8, minus 7, 4, 2, 0, 1. And again, I'm going to expand along that second column there, so I delete the second row, second column, and I'm going to get, well, 1 over 7 cubed times minus 7 minus 1 to the 2 plus 2, and the remaining determinant I get 3 minus 2, 2, 1. So out front I've got minus 1 over 7 squared times 3 plus 4 times 7, I get minus 1 over 7, which is 1 over the determinant of A. So it works in this example. Good. All right. Now, a few videos back, we also introduced the transpose. Okay, so the determinant of the transpose is the same as the determinant of the original matrix. And the reason why this is true, so this is basically true since we can expand along columns instead of rows. Okay? And so if we computed the determinant using kind of row expansions at every step, and then we computed the determinant of the transpose using column expansions at every step, we would be doing the exact same thing. We would get the same result. Okay, and the consequence here is that we can, we know that we can't do column operations when we're trying to simplify a system, because, adding a multiple of a column to another or multiplying a column by a constant or swapping columns, right? That changes the variables around. Like swapping two columns would mean interchanging the roles of, say, x and y in your system. You don't want to do that. You want to keep those columns where they are so that you can keep track of the variables. But here we're not solving a system, we're computing a determinant, and we know that basically a column operation on A, let's say, is the same as a row operation on a transpose and vice versa. A row operation on A is the same thing as a column operation on the transpose. So you can do column operations instead of row operations if you want. So for example, in this matrix here, let's say I wanted to compute this determinant, right? So if I wanted to calculate the determinant of A, right? Well, I could use this leading one in the corner to get rid of the 4 and the minus 5, but those are, I have to do 2 row operations, and I'm multiplying by a minus 4 and a plus 5. They're somewhat larger multiples. I mean, it's not that bad, but there's a bit of work involved there. Similarly, I could use the 1 to get rid of the 3, but the easiest thing to do here is I can do column 2 plus column 1 and make that my new column 2. So I add column 1 to column 2, and that's a type 3 column operation. And that just as a type 3 row operation does not affect the determinant. A type 3 column operation also does not affect the determinant. So I can do that column operation, and then I get 1, 4, minus 5, and then 0, 2, minus 3. I'm just adding column 1 to column 2. 0, 3, 1. And then I can expand along the first row, and I get 1, it's a plus sign, 2, 3, minus 3, 1. So 2 plus 9, I get 11, right? And if the column operations make you uneasy, you can always argue it this way. You could say the determinant of A is equal to the determinant of A transpose. So we do the transpose 1 minus 1, 0, 4 minus 2, 3, minus 5, 2, 1, right? And then we can do a row operation. Row 2 plus row 1 into row 2. And we get 1, 4, minus 5, 0, 2, minus 3, 0, 3, 1, and we get that same value of 11 as before. Okay, so that's it for sort of properties and computational methods with determinants. In the next couple of videos, we're going to explore a couple of, well, we'll call them applications, but they're really applications to other aspects of linear algebra, right? So we're not leaving the world of linear algebra. We're going to see that there's a couple of things that we can do with determinants.